All right, so let's go ahead and talk about another space within a vector space. So that's going to be the null space. And the null space is any time that you have a matrix, okay, m by n, then the solution set that takes A times that solution set and takes it into the zero vector, we call that the null space. So if you have independent vectors that make up your matrix, like an n by n, where the columns are all independent, then that null space is just going to be the zero vector, right? It's going to be the trivial set. So that is possible. We have a visual here of this set, this null space. So we call it null A, which is 1L, and it's the set of all x vectors in Rn that take A and map it to the zero vector. Okay, so that zero vector of Rm, because x is in Rn, so if we take Ax, and this is an m by n, and x is an Rn, so that's an n by 1, then our zero vector is going to be an m by 1. So that's why this is going to be in the Rm space. So let's look at an example. So for the matrix above in 2, and I'll scroll up here in just a second, determine if this is in the null space. Well, if that's true, then when we multiply, we should get 0. So let's go ahead and copy down A. So A is 1, -5, -3, 9, and -2, 1. And if U is in this null space, then if I multiply by 5, 3, -2, then I should end up getting a 2 by 1 that is the zero vector. So let's multiply column and row, or row by column, I should say. 1 times 5 plus -3 times 3 plus -2 times -2. So that does give me a 0 here. Let's look at the bottom. -5 times 5 plus 9 times 3 plus 1 times -2, and that gives me 0. So yes, this is in the null space because it gives me the zero vector. So U is a vector in the null space. Which brings us to a theorem here in the book. So the null space of an m by n matrix, remember, so any vector x such that Ax equals 0 is what we're talking about. That null space is a subspace of Rn. So these vectors x meet the definition of a subspace in Rn. So all solutions of x equals 0, m homogeneous linear equations, because remember A is an m by n, with n unknowns, is going to end up being a subspace. So the solutions make a subspace of Rn. Let's look at an example of that. So if we let H be the set of all vectors whose A, B, and C satisfy these two things, show that H is a subspace of R4. So what we can do here is we're going to make this a homogeneous system by saying A minus 2B plus 5C minus D equals 0, and negative B minus A, I'm going to move over there, plus C equals 0. And so this is a homogeneous linear system. And we could write this as A being 1, 2, 5, -1, -1, -1, -1, 1, 0. times a solution vector equals 0. And so x here, as this solution vector, is a solution to ax equals 0. And so therefore, by this theorem, this must be a subspace of R4. All right, let's look at another example. Find a spanning set of the null space for this matrix. So the first thing that we're going to do is we're going to augment this matrix with the zeros. And we're trying to figure out the solution set in which this is going to be true. Now, with some row reduction operations, we end up getting this as our reduced matrix. With that last row completely zeroed out. All right, so let's go ahead and let's let x4 and x5 be our free variables. That means that x3 must be equal to negative 2x4 plus 2x5. It also must be true that x2 is free, and that means that x1 must be 2x2 plus x4 minus 3x5. So let's write this as a spanning set. So x must be equal to, here's x1, that should be a 4. Hold on one second. 2x2 plus x4. Okay, x2 is free. x3 is negative 2x4 plus 2x5. And then x4, x5 are free. I'm running out of room here. Let's write this as a spanning set. So that means we can say that x2 is multiplied by the vector 2, 1, 0, 0, 0. x4 would be 1, 0, negative 2, 1, 0. And x5 would be negative 3, 0, 2, 0, 1. Now, one thing that we can do is we can give each one of these vectors like just a new name. So we could call this like vector u, we could call this vector v, we could call this vector w. And so we could say maybe up here in some space that like x as the spanning set is x2 times the u vector plus x4 times the v vector plus x5 times our w vector. And then any linear combination of this for any values of x2, x4, x5, since those are free variables, these would all end up being in the null set of A.